These are the notes for AP Chemistry, pages 25 and 26. Most of what needs to be covered is just typed in here already. And if you look at this first page, 25, you'll see there's just a lot of info on one page. So I'm not going to waste your time going through all the minutia. You can read it on your own. I'll hit the good stuff. So first thing is you should review your intermolecular forces, like I've mentioned up at the top, up here. If you've not done that recently, review your intermolecular forces again, because that's going to be useful. The four types of solids are named after the type of bonding, so let the name help you. First one I have here is covalent molecular, meaning you have individual molecules. Ionic, and then down here I have covalent network, and let that help you. Network means that the atoms are networked. So you don't have individual molecules here. You have a bunch of atoms all stuck together in some way, making a huge network, hence the name. And at the very bottom, I have metallic, which of course is talking about metals. For convenience, notice that the notes, it's the second item that is always unique. So in the case of covalent molecular, the unique thing is that they have fairly low melting and boiling points compared to the other solids. Ionic, they do not conduct electricity in the solid form, but they do if they're liquid or if they're dissolved in water. In the case of covalent network, they have very high melting points. And in the case of metallic, they conduct electricity in all forms. And when it comes to conducting electricity, it's important for you to know what it is that's conducting. And so there always has to be a moving charge. So when something ionic conducts, it is because you've got mobile charged particles. In the case of metallic, it's because you have moving electrons that can flow from atom to atom or ion to ion, depending on how you look at it. A couple of specifics. Here I've included a picture of what's called a crystal lattice for ionic substances. I have that over here. And it's important in ionic things that you realize when you see a formula like NaCl, that's not a molecule. That is simply just a ratio telling you that for every one sodium, there's one chlorine. And they just keep going in all three dimensions in that pattern. In this particular case, every sodium is surrounded by a chlorine, and every chlorine is surrounded by a bunch of sodiums. So be careful, this is not a molecule. You want to call it a formula unit or crystal lattice. In the case of covalent network, one of the more interesting situations is what's called the allotropes of carbon, in which you have diamond and graphite are the two most common. It's interesting to note that diamond is so hard because it's strong in all three dimensions, whereas graphite is weak in one of the dimensions. And I have a drawing of it here. And what this is trying to highlight is in a sheet, so say this sheet at the top, this one up here, all those are covalent bonds. Those are very strong. Likewise, there's a sheet down here, same idea. But holding the two sheets together, as I have labeled, are weak London dispersion forces. And that's what's actually ripping when you use a pencil. As you write with a pencil, you're ripping these sheets apart. Same exact stuff as diamond, it just is arranged in a way that has a weak dimension. Now, buckyballs is something discovered fairly recently in which it forms an actual ball shape. The classic version has 60 carbons arranged like a classic soccer ball, the way it's sewn together, in which the pattern is that every pentagon is surrounded by 5 hexagons, and every hexagon is surrounded by alternating pentagons and hexagons. And it's an interesting geometry. Now, this ball can be stretched out into what are called nanotubes, and it's something that you might be seeing in the future regarding materials being made out of these. Some people say there's a 4th allotrope called graphene. And it is just a single sheet of graphite. So it would be taking just the one sheet. And it is said to be as close as we can get to a 2-dimensional object. Now, it isn't 2-dimensional. It does have a thickness of 1 atom, but it's getting close. And there's an interesting story behind its discovery and uses. It's actually being researched right now to be used for a variety of electronic applications. I have a note here about alloys. There's a couple different types of alloys to be aware of. And again, let the name help you. The name tells you what they are. In a substitutional alloy, some atom is being substituted for another. And in what's called an interstitial, at least that's the way I say it here, no atoms are being replaced. You're putting smaller atoms in between the larger atoms where there are spaces available. Now, moving to liquids past the solids, I have this silly phrase here. And this just comes from a meme that was popular years ago, in which, if you look at the definition of a liquid, liquids take the shape of their container, but they keep a constant volume. And so it's been noted if you put a cat in a container like this, its hair kind of takes up the shape of the container. So according to that definition, cats are liquids. It's just kind of fun. All right, things we've talked about before that are important to remember here is the concept of vapor pressure. As a liquid evaporates or boils, it gives off vapor, and that vapor creates a pressure. Moving to the next page, I've got what's known as liquid vapor equilibrium. And it's a good idea to get this picture in your head that I have right here. Think of a closed container with some liquid and some gas. The liquid is still vaporizing like that, but at the same rate, the gas is liquefying. So to an outside observer, the amount of liquid and the amount of gas are constant. But if you had special magnifying eyes and you zoomed into a single particle, you might see that particle change its state. But of course, there's another particle changing the opposite state. So that's why the amounts don't change. We've talked about boiling before, but I go back into it here. Things boil when their vapor pressure is able to compete with the atmosphere. And that's why water boils at a lower temperature in the mountains. Everything boils at a lower temperature in the mountains. And it's possible, if you get the atmosphere low enough, you can actually boil water at room temperature. So you can have boiling water in which it's not hot at all. But of course, you have to modify the atmosphere and put in a pretty strong vacuum to make that happen. Here's an example calculation. It's a very polite example. It says to consider. It doesn't tell you to do it. It just, please consider. We have 1 gram of liquid water at roughly room temperature. The sample is introduced. So it's still a very polite problem. It's introduced. It's not just shoved into a 10-liter flask. It's introduced to the flask. How much liquid will remain when equilibrium is established? And equilibrium here is not referring to a reaction, it's referring to the liquid vapor equilibrium. Okay, well, what we can do is calculate under these conditions how many moles of gas has become vapor. And so I do that here using the ideal gas law, no surprise. I then take the moles, convert it to grams. That's the grams of water vapor. The question didn't want to know how much became water vapor. It wanted to know how much remained liquid. So we subtract that from the total at the beginning, and we get the amount of vapor. Sorry, not the amount of vapor, the amount of liquid water that remains. Let's see. If we go to this summary number 3, this is a pretty important problem. As I put my little symbol next to it of the little eggmobile. It says to rank these liquids according to boiling point. In this case, I said from highest to lowest. And I've given a list of things to look at. The first thing you want to look at is the type of bonding. In this case, they're all covalent, or in the case of helium, it's an atom. And so this one stands out. It's the ionic one. Now, without knowing anything else, the ionic one is definitely going to be the highest. So we now know that number 1 is the ionic one, calcium chloride. Next, you want to look at the shapes, which I have listed. The shape doesn't tell you anything about where it boils, but it gets you prepared to now talk about polarity. So then we did polarity. Polarity itself doesn't tell you about boiling, but that gets you ready to talk about intermolecular forces. And now we can really start getting down to business. You'll notice that both water and ammonia have all 3 intermolecular forces. So in this case, what you have to look at is which one has stronger forces of the 3. Well, because water's more polar, its dipole-dipole force will be stronger. And so that's why this one wins. And we now have number 2 settled here. And then this one falls into place in number 3. Among the remaining 3, CO2, helium, and CH4, they all only have LDF. So just LDF, LDF, and LDF. In this case, you want to look at how many electrons each has. The one with the most electrons is the more polarizable, meaning the electrons can be more on one side of the molecule than the other, or more on one side of the atom than the other in the case of helium. And we typically don't bother counting electrons. We usually just look at the molar mass. And whoever has the higher molar mass will have more electrons, and that's just a quick way of doing it without having to go through electron configurations. The higher the molar mass, the more electrons it has, so the more polarizable it is, and that means it has a stronger LDF. So next in line would be CO2, CH4, and no surprise, helium is last. And if you look at my ranking here, you might notice that between calcium chloride and water, I went crazy and I did extra greater than signs. That's just emphasizing what a huge jump it is when you go from covalently bonded molecules, which have intermolecular forces, to ionically bonded ions, making a crystal lattice. And I've actually looked up the values, and if you look at them, you can see 1935 is quite dramatic over the rest. And then the rest all fall into place. You can see that helium, it's just above absolute zero, -273, which means the forces holding it together are amazingly weak.